that's my second lecture. I still have to deal with the rest of the first lecture. I want to talk I want to finish a story about Coulomb blockade. All right. Okay. There was a question. Could you please suggest textbooks or textbooks with problems and solutions related additional to my lectures for self-study purposes? Well, that gives me a little bit shining opportunity to advertise my own book, me and Jaroslav Blanter, Quantum Transport Introduction to Nanoscience. Just like this. If you Google it, you get the book. Fine. Coulomb blockade. So what do we have? We have an island which can host integer number of charges with a metal with which we can supply charges to this island. And we have a gate which can, which is biased with respect to this metal electrode, right? What's going on? You bias it, you create some electric field between the electrode and the gate, which means that the charge of the island wants to be bigger, all right? However, it cannot be bigger continuously. It cannot be like this. In that case, we would have the smallest electrostatic energy, right? This can be written as this energy. So the charge stored in the island is always integer, while it wants to be equal to continuous charge induced by the gate. All right, one can compute this electrostatic energy, basically taking two capacitors, capacitance to the electrode, capacitance to the gate, and do algebra. Okay, what does it mean? Let me just plot this energy. We will see this picture again. Let me just plot this energy versus gate voltage at different ends. Okay, it's a simple plot. In fact, I've got parabolas. I've got parabolas which are shifted horizontally, corresponding to different ends. I want to get minimum energy from this parabola. So that's what I do. I just draw orange line through lowermost pieces of this parabolas. So I get the ground state energy. Now I want to plot the charge versus gate voltage. And you see, when I move along this axis, I go from one parabola to another parabola. So the charge just increases in step-like fashion. This is how to realize, how to see charge quantization in a single electron box. I should say, again, it was a response to a previous question, that this quantization is classical. It just relies on the fact that number of particles in an isolated island is integer. Fine. Let me understand it in more detail. What does it mean that island is isolated? Well, in practical terms, if we deal with metallic systems, and frequently we do, the mean to provide isolation is to make tunnel barriers between the island and the metallic electrode. You don't have to do it with a gate. The gate you could just put apart. You don't need electric contact. Right, how to do this? Well, there's way to fabricate such systems, which is already like several decades old. Well, first you do the leads evaporated on a substrate. Then you oxidize the leads, forming oxide barrier. And then you just put in the next cycle of evaporation, put an island on the top of it like this. What is formed is called overlap tunnel junction. You want to make it smaller for capacitance to be smaller, for charging energy to be bigger. Okay, one can wonder what is actually how thick should it be? How good is the isolation? It is simple to envisage two limits. Well, if it is too strong of the barrier, then electron transfers would happen once per week. That's probably not what you want. If you make it too strong of coupling, then perhaps you could have a shortcut. And in this case, you cannot really separate your island from the rest of the metal. You're gonna lose integrity of your charge. Good. One needs kind of more reasonable criteria. And this criterion is derived in a very funny way. I want to mention it from a combination of a quantum argument and very classical argument related to RC properties of the circuit. Good. So this is an island which is characterized by contact resistance R and capacitance C. And RC time is a typical time to charge or discharge this island. Well, let us now involve a Heisenberg uncertainty relation. Energy, which is charge and energy of the system under consideration, should satisfy Heisenberg relation. Energy times time has to be bigger than h bar in order for energy to be well defined. Well defined charge and energy is just what we want. Charge quantization. Right? Okay, we substitute here charge and energy, we substitute RC time. What you get, we get a condition on a resistance of the contact between the island and the metallic electrode. Good, it appears to be fundamental constant called conductance quantum or resistance quantum, doesn't matter for us. It's several tenths of kilo ohm. Right, that's one most important requirement. Also, in order to see Coulomb blockade, you have to make sure that your temperature and voltage are small on a Coulomb blockade scale. All right, I've done Coulomb blockade. Now I am going to second lecture. I have to switch my transparencies. Right. 2, lecture 2. Here we are. So what I'm going to do now is to combine Josephson effect and Coulomb blockade and get superconducting quantum mechanics. Sometimes I call it homemade quantum mechanics. I will explain why. The basic unit, a new artificial atom, if you want, would be superconducting island. And I will go around the system for a while to explain why it actually represents quantum system. I will just quantize it in place if you wish. Good. Then once I quantize it, I can write a Schrödinger equation and discuss it. We will discuss the properties of this artificial atom in 2 different limits. Good. And that will bring us very close to practical devices, which are made in this way. I will react on this. And that will bring us to actual qubits made on this device. I will discuss some designs of the qubits, which, if one takes it very practically, have more historic value than practical one. Nowadays, everybody does this Transmont stuff, but we also not talking about qubits only. We are talking about superconducting hardware. So I guess it will be instructive to look at all the qubits designs to understand what one can do with the system in under consideration. All right, Zoom control Windows do something bad with my screen. I could keep the charts on the left. I could switch off one of the windows. Is it better now? Is my window totally visible?
Actually, not. In the very top, there is some long rectangular. Yes, this one.
Oh, that I'm afraid I cannot do anything with this. Let us see. You mean that?
Yes, exactly. If you move it in some left or right side, it will be fine. But here is
have
yeah.
problem with this. Okay, perhaps I can keep it like this. It's kind of best solution I can come with.
Yeah, actually, now it's slightly yeah. The half of the top screen is hid by this.
Yeah, but I've no information in this part, so I guess it will be fine.
Yeah, now it's totally fine. Thank you very much.
Great. So let's go on. Let's go on. Homemade quantum mechanics. We take 2 things we just whatever learned or repeat. We take Coulomb blockade in normal metal. And as I mentioned, in this case, we have discrete states, but the classical discrete states very much like sides of a dice or something like that. There is no quantum coherence. Why is it so? Because they are states in normal metal. And in normal metal, you can excite the state with very tiny energy. To create, for instance, electron-hole pair will be the state with the same charge, but very different quantum mechanically. That's why this state is classical. It can be presented as a quantum state in many, many ways. That's not what we want. In this case, we don't have quantum coherence. And this is superconductivity, this marvelous discovery, unpredicted and unpredictable, which can solve the problem, which brings coherence for us. And if we combine Coulomb blockade and Josephson effect, the charge states really become quantum mechanical states. You can realize superpositions of the states with different charge, which means that one can realize an individual quantum state at the typical size of these devices, of these Josephson junctions, Coulomb islands. And that appears to be micrometer scale. If you're talking about individual particles, individual electrons, which are present in your device at this scale, that would be billions and billions. Nevertheless, the whole multitude of these electrons and atoms is coordinated into a single quantum state. Good. Homemade, eventually, perhaps it does not readily come into sight, but you can work at micrometer scale at home. Sorry for experimenters who are asking for multi-million grants. Of course, you need it to produce really reliable and highly technological nano devices. But in principle, you can do it at home. There are people who, for instance, write Holy Scripture on a rice grain. And what you need for that, and this is a work at micrometer scale, and what you need for that is just investment of $200 to a good microscope, and you have to buy a good grip device. That's also like $15. And then you just take a grain of sand, and that provides you with a necessary tool to work at home at micrometer scale. You could try Josephson junction in such a way. Homemade quantum mechanics, which kind of revolutionized our relation with quantum mechanics. Since this technological advances, we don't have to go to atomic level to study quantum phenomena. Complete revolution, which still remains largely underestimated. Fine. Let me see how does it come about. Why it is quantum mechanical after all? First of all, let me remake a system which I just showed. It is a superconducting electron box, or they call it Cooper pair box. It is a setup which was just made superconducting. Superconductivity is not important for the gate electrode, of course, because there is no electric connection, but both main electrode and ions, they became superconducting. What has changed? Now the contact between two superconductors became a Josephson link. Josephson link provides charge transfer. So associated energy is Josephson energy. As we have learned before, it's just cosine-like function of the phase. In addition to that, we have this the fact I just explained. We have Coulomb energy, which means that there's also charge and energy scale, and this function of number of charges in the island. Fine. At the moment, both phi and number of charges are classical quantities. I want to do some metrics. I want to make them quantum. Just keep it with me. Okay, there is a general prescription how one quantize a system. All right, it's a theoretical exercise. You can hardly do it in practice to make a system, a quantum system from classical one. Let's see how does it go theoretically. Yeah, I will, Valentin, I will react on your question. Just let me formulate what I wanted to say. Replace classical variables by operators. Kind of put hats on the top of this phi becomes an operator. Then those operators, they could not commute. One would have to postulate commutation relations between these operators. That's a kind of creative part. One could go crazy. One could postulate whatever relations what they want. But then there is a very certain way to derive quantum dynamical equations from the Hamiltonian and definition of the operators. One has to do this job and see if quantum equations reproduce classical equations of motion. The question of Valentin, do you know the less phenomenological and more rigorous procedure of the quantization for this system? Yes, Valentin, I do know, but the result of application of this procedure, which remains phenomenological, although it is less phenomenological, and which still has loopholes, although it's more rigorous. The result of application of this procedure is precisely the same. There are no observable consequences for this. That's why I prefer to go do it in a very plain fashion. It makes it more instructive, because once you see that, you might say you get a bit paranoid and learn to see quantum mechanics in any system, just in any system you look at. Let's see how does it go. I want to simplify a bit energy, which I deal with. Instead of cosine phi, I would like to use expansion of this energy at small phi's. And in charge and energy, I just keep the gate electrode for simplicity. So I have a kind of simpler energy, only quadratic terms. That's going to be energy, that's going to be Hamiltonian. Next step, I'm going to derive classical equations of motion in the system. Just keep with me, there are several steps, but all of them are simple. Derivative of charge. That has to be current, so superconducting link. Current is a sign of phase. We keep phase small. So this is it. Josephson relation. I also gonna use it as an evolution equation for phase. And not to forget, there is a relation between charge at the capacitor and voltage at the capacitor. All right, I combine those two. And then for these classical equations, I would like to use some fancy quantum notations. Quantized charge in units of charge quantum, a number of particles. Right, Josephson energy instead of critical current that contains H bar. And write charging energy instead of capacitance. What's the use of it? I got very symmetric form of the resulting equations. They're still classical. They're linear equations, simple to work with. But to make them quantum, we will postulate that operator of charge of number of particles and operator of phase satisfy canonical commutation relation with a yet unknown parameter alpha. A piece of inspiration for that these two, a little bit like momentum and coordinate in quantum mechanics of single particle, and the commutator is a constant, h bar. Right, Valentin, there is multiple answers to your question. I will address it in several transparencies. Quantum equations of the usual value. I compute corresponding operator is the Hamiltonian. It's Heisenberg equation of motion, universal for all quantum mechanical systems. Okay, with the help of this, you can do commutations. And what I see that these quantum equations reproduce classical equations if alpha is set to minus 2i. Here we are. We have quantized our system, Josephson and Josephson effect plus Coulomb blockade, charge, and superconducting phase. Right? I want to have a little bit of spoil. In fact, when I did simplifications like this, I have reduced the problem to an oscillator. Look at linear equations for two components. If I solve it, one just get oscillations at a certain frequency. It is in fact an oscillator. And partial answer to question of Valentin, any oscillator, whatever you make it from, superconducting circuit, nano-optical system, nanomechanical system. You could try to make it from wood, whatever. Any oscillator is quantized in a very certain manner, well, more or less as I described. So eventually any oscillator, if you look carefully, is a quantum system. The only problem that sometimes fluctuations of this oscillator are too big. The level space in the oscillator is too small to be resolved at a given temperature. So one cannot really localize this oscillator in a singular quantum state. With superconducting oscillators that work, those are in a good parameter region. Well, I'm done with quantization. Let me just try to use this relation. Let me try to get some intuition presenting these operators like something familiar to us, familiar from elementary quantum mechanics course. Look, this and it might seem like momentum, right? And momentum in a representation where phase is diagonal is represented as a derivative of this phase. This is representation of charge in representation where phase is diagonal. I want to do reverse joke. I want to represent phi in terms of charges in charge space. And then I guess that I want to represent a different operator. Because, yeah, look, in Johnson energies, I have just sum of two exponents of this kind. And this exponent, a single exponent, is eventually a shift. It is a shift in charge by two. Two, because I transfer Cooper pairs, I transfer two elementary charges. So if I just take superconducting state and multiply it with a phase factor, I got the same state with one extra Cooper pair. All right, good. I did my magic. Everybody who wants to have more detail about this trick, please ask me now. Because from now on, I will write Schrödinger equation. I will do usual quantum work. Good, then I go on. I write Schrödinger equation. I will do it in two representations. Those are completely equivalent and like I could call it coordinate representation. And this is momentum representation. And as in quantum mechanics of a single particle, wave functions in one representation are obtained from wave functions in another representation by applying Fourier transform. Right. Let me first talk about phase representation. Okay. It is a Schrödinger equation for eigenstates of an operator, for eigenstates of a Hamiltonian. This Hamiltonian is made from Josephson energy, and there in phase representation just diagonal operator with elements which are cosines phi. Good, and this is charge and energy. So I replaced N is momentum, and this gate, the effect of gate charge, it looks like vector potential of magnetic field, which I added to this equation. Otherwise, it would be just kinetic energy of the particle, p squared divided by 2m. Fine. I can rewrite it in charge representation. In this case, the charge and energy is diagonal operator in charge space. And Josephson energy works like we just have seen. It shifts wave function by either plus or minus 1. So it really describes a transfer of Coulomb, quantum coherent transfer of Cooper pair through the contact either in one or opposite direction. Good. We have some question. We could bring it to a mathematician to solve it for us, to draw the conclusions, while mathematician would refuse the problem. What is this? What is going on? We don't specify yet boundary conditions. We don't know how these functions of the phase would like. And there are two possible answers to this question. First answer, I just define phase on an interval from minus pi to 2 pi. And I glue these points. So in fact, phase would be defined on a closed manifold, if you wish. What would be the best representation for this manifold? Suppose you have a cylinder. And well, gravitational field in this direction. And suppose you have a cut to this cylinder by a tilted plane. Right? That's the position of the cut. And the angle will be just the phase. And eventually, if one takes a gravitational potential into account, it will have the same form, cosine phi. All right, that's one of the possible answers to the boundary conditions. Another answer is just letter 3. Let this phase to be unconstrained. Let it to change between plus and minus infinity. Then what we have is a particle in periodic potential. Like, recall your first solid state course. And there's a particle propagating in this potential. So there will be so-called Bloch states. Question: can we understand the first excited state 2 as a state with an extra Cooper pair on the island? Yes, one can say so. So it's about the basis in this charge representation. In this case, all states I could number with a number of Cooper pairs, extra Cooper pairs in the island. And also man is 2, man is 4, and so on. We will look at the energies of the states in a moment. I want to stress once again that for the same equation, we could have 2 boundary conditions. So what to choose? It appears to be that both answers are valid, but for different devices, for physically different devices. The condition of periodicity imposed on the phase, on the wave function of phase, leads to quantized charge. And as such, it describes a superconducting island, finite volume, which is connected to the bulk electrode. Right? How one can see that charge is quantized in this case, just throw away Johnson energy. Then we have only charging energy, which is kinetic energy, and for purely kinetic energy, eigenstates of the systems are just plane waves with quantized momentum. Here we are. As to opposite choice of boundary conditions, it's a device when we just have Johnson junction, but both electrodes are bulk electrodes. In this case, there is no charge quantization. Charge is continuous. And in fact, answer for wave functions are Bloch waves. They can differ in what is called quasi-charge. It's analogous to quasi momentum in solid state theory. Again, if one forgets about charge and energy, one gets explicit wave functions of these states with certain charge. All right, good. We set a question which has been teasing for mathematical increment series for a while. It's also kind of practical question. You want to put it into computer, you don't know what are boundary conditions. We sort it out. So in fact, we talk about 2 different devices. Right. And this answers one of the questions of Valentin. There is indeed a problem with the definition of the phase operator. We understand that exponent of the phase operator is pretty much certain. It is a charge transfer. If one takes log of this, one can have 2 different situations, physically different. One can define phase operator on a closed circle, and one describes device A. Or one can define it differently, and one describes device B. So whatever definition you make, no mistake, but just your definitions are applied to physically different systems. Good, Valentin, does it answer your question to some extent? Fine. Now I have this superconducting island, which is in fact a rather fundamental building block of all Josephson devices, very much like an atom, hydrogen atom, whatever helium atom, is a building block of quantum systems at atomic scale. So what I want to understand now is how does it work? What are characteristics of the spectrum of this artificial atom in different limits? What are limits? Let me recall that in the whole energy, I have two energy scales, charging energy and Josephson energy. So the only limits which I can draw is to set it either this one in this way or in opposite way. I start with a well, rather boring limit when charging energy is dominant. Charging energy is dominant, and what does it mean? It means that we are very much like in a classical single electron box, with the only difference that now we catch Kuiper pairs rather than single electrons. So eigenstates of the system are mostly states with a definite charge. That's why I took the same picture of parabolas, which are used for Coulomb blockade, and just plotted only even parabolas. Good. It is, I would say, boring and even unpractical for most of points, except points of intersection. So what's going on in this case? In this case, the energies of two charging states become the same, become degenerate. And in quantum mechanics, the degeneracy situation is very unstable. It means that even tiny charms in the Hamiltonian would play a role. That happens here. So let me perhaps sketch some simple Hamiltonian. We take a Hamiltonian, we take only two states, blue and red. Near this point, we have energies of the states. All right, so sometimes if epsilon is positive, then blue state wins, otherwise, no, sorry, I did a bit differently. Let me talk about these two states. Crossing. Right. So now what Cooper pairs, what adjacent energy is supposed to do? It's supposed to couple these states, like electrons and holes are coupled in superconductor in the beginning of this lecture. So it induces non-diagonal matrix element in this simple Hamiltonian. Good. What we get from this, the energy levels are plus minus. Hyperplus. That's what I plot here. And right in the middle, the eigenstates are equal weight superpositions of two different charging states. Good. So simplest realization of superposition, very clean one. Only two states with closest energies are involved. Right. So that's about the limit of large energy. I think I would appreciate a short break. So why don't we have 4 minutes break, right? I'm on again.
Thank you. Please start.
Superconducting island, opposite regime, opposite limit, and now we have dominating Josephson energy much because I'm charging energy. The spectrum looks much more complex. But anyway, just give me a chance to explain it. Let me first kind of sketch over here the profile of cosine potential. Okay. Right. High potential. And if I keep it infinitely high, well, the particle would have a chance to live only here, at least in the ground state. What will happen if I kind of kick it? It will oscillate. And the mass corresponding to the oscillator would be given by charge and energy. So in fact, the frequency of these oscillations would be, how do we call it, geometric mean between charge and energy and Josephson energy. That's what we call plasma frequency in the end of second lecture. What does it mean? There will be equidistant levels in this oscillator potential. Right. It's not parabolic. That's why it's not precisely equidistant. The higher the levels, the more is the distance. Well, at some stage, you exceed this potential barrier. In this case, well, we still have an island, so the phase space is compactified like this, which means that we have something which is similar to plane waves, quantized momentum, and indeed upon rising energy, we see that the resulting states become closer and closer to parabolic ones at this transparency. So a bit more complicated spectrum, localized levels, equidistant at lower energies, and charge states at higher energy, much higher than the Josephson barrier. Good. That is a kind of quick description of superconducting band. Elementary atom in homemade quantum mechanics. Let us first look at First ever quantum effect, which has been predicted, which is not that difficult, but that has been also observed. Quick control question. When it was observed? So, control question. Who has A? Oh, that was too quick. You guessed it correctly. That was somewhere quite some time ago. It was not that year when Josephson effect has not been yet discovered. It was not that year when we have already pretty much sophisticated qubits. It was the first observation. So what is to observe? It's about Washboard potential again. And now we recognize, I don't remember if Martinez was a co-author. It could have been Webb was there. That's for sure.
He was the co-author.
Good, great. He has to be a PhD student by that time.
He was a PhD student in Berkeley in the group of John Clark.
Yep, precisely. Good. So what was the setup? Just the same Washboard potential. Let us recall that we can have at low current distant minima, and the particle can be in one of these minima. We can consider quantum mechanical tunneling through this potential barrier. Of course, if the barrier is big, it's very weak, but if one brings the system closer to this critical current, the barriers would become smaller, and then at some stage, you would see quantum mechanical tunneling through this barrier. It was quite some work to distinguish it from thermally activated tunneling. That required indeed complex setups and much experimental work, but that was the pioneering observation of quantum effects in Josephson circuits. Fine, it was single junction, nor single island. So one could wonder if one can really make atoms out of that. I will soon answer that. The answer is positive, but let's go step by step. Let me confess some cheating, somehow important for understanding this chance. I kind of told you that from now on, number of electrons is odd, because is even because it's transposed by Cooper pairs. But I didn't say why. The reason for that is that if the number of electrons in your island is odd, it requires extra energy cost. What for cost? It is just superconducting gap. If one increases, if one puts an extra charge into superconducting island, okay, let's sketch it. No states, one's a gap, there's a gap. One has to put it somewhere. One cannot put it into condensate. One needs to create a quasi-particle, and quasi-particle cost is always delta. One can add another quasi-particle. In this case, they can form a Cooper pair and go back. So there is an odd-even energy difference, which actually also, one can say, enables applications of superconductivity. In all devices available, one can, in one or another way, neglect odd electron states. Parity effect. Right. Now I can go to qubit realizations. We'll go through several ones, and the order is more or less historic. Charge qubit. Charging energy dominates, so I just copied the picture you have already seen. Cooper pair box. And there's very little quantum mechanics in there, except this particular point. What's good about this gate voltage is a freely available parameter. One can always tune it to this point. Experimental realization, first superconducting device. So there were some fine and interesting things. I don't think I have time to go through all details. Let me just mention main elements of the setup. One needs to have an electron box, and on this photo here, one finds a box. As I explained, it was imposed as a metal evaporated film on the top of the contacts. These things are superconductors. The loop will allow you to tune Josephson energy, the energy of Josephson link between the box and the reservoir. Well, it was about operation with charge states. So in this case, you not only want to operate your device, you want to provide a readout. This readout was pretty much invasive, but robust and very convenient. It was a probe attached to the setup, and any time you are in a charge state of upper energy, it will decay to the probe and give you current in the probe. Good. What was the operation scheme? What you see here on this picture are hyperbolic levels I showed to you several minutes ago. Right? So they're split in some point of gate voltage. The splitting is given by Josephson energy. Operational point of the device cycle was eventually somewhere far from this point. And here, the authors have been sure that it's in a given charge state. Okay, charge state 0 at this side. Then what they did, they apply a pulse which brings it quickly to this point, and that pulse has certain duration, delta t. So what one expects, the system is in a state 0, while Hamiltonian dictates, well, you've got to be in a superposition of two states. Initial state cannot choose between them. And what happens are oscillations, so-called Rabi oscillations, with a period which is given by this Josephson energy. That's what has been observed in the current through the probe as a function of pulse duration. These oscillations were the first signature of operational qubit. Charge qubit. Simple kind of, how to call it, minimalistic concept. You just take only two states and you do this. It appears to be that although these qubits are very convenient, they are obviously sensitive to charge noise. And that appeared to be a problem, purely technological problem. I wished there were no charge noise because these qubits are conceptually simple, easy to make. The current conclusion is that they are not that suitable to make practical qubits. So people went to different directions. Right, this is, as you know, John Martinez didn't quit after a successful PhD. He went on, and there was another qubit scheme, which is called phase qubit. He could reuse his PhD project for that. So it's the same single current biased large Josephson junction. It's quite opposite parameter region. E.g. is enormous in comparison with charging energy. Let us recall what we have. It's a single well of a Weisbord potential. There is a quantization of the states in this well, and the parameters are chosen such that there are three states which are there in this level. Eventually, all these three states are not true quantum states. A purist would reject this qubit design. Why is it so? Because there is always a possibility to tunnel through this barrier. And once it tunnels, it just goes on and on and on. The system is out of equilibrium. It has to be readjusted again to stop in one of the potential minima. It is good to detect the states. And the parameters were chosen such that the decay from level 2 is very quick, while the decay rates from these states are negligible. All right, so these two were used as two states of a qubit. What to do with this qubit and how to measure this qubit. Manipulation was pretty much the same as it is done since invention of magnetic resonance. You apply a pulse of resonant microwaves, which are in resonance with this energy difference, and changing the duration of the pulse, one can rotate qubit states to any superposition. All right, you can rotate this, but you also want to check whether you rotate it correctly. You want to prove that your qubit works. So how to read out? That's kind of a very fine model of readout. In this case, one applies resonant pulse between to matching energy difference between 1 and 2. So if you have some probability to be in the state 1, it is transferred to the probability to be in the stage 2, and it gives to fast decay, and it gives to measurable voltage pulse at the junction. So in fact, they could achieve single-shot measurement of this probability, so they could prove that it's really qubit, decent qubit, with decent decoherence and decay rates. One of the first qubits which has been calculated. There were difficulties to achieve quantum gates to make more qubits of this sort to talk to each other. That's why another qubit design has been involved, and which is again got a name tag, so-called flux qubit. And the idea was as follows. Usual Josephson potential has single minima. It would be funny to arrange a system when there are two minima close to each other, separated by a small distance. Then the states which would form quantum superposition are the states which are either in the left or in the right minimum. Good. How to make it from Josephson junction? Rather old idea about that time was to take a junction and to put it into inductive loop. What would be energy in this loop? It would contain Josephson term plus quadratic term corresponding to this inductance. And then one chooses inductance in such a way that the negative inductance in this point is compensated by positive inductance of the loop. And somewhere in this point, the potential becomes very flat, and it can be tuned to having two minima like this. Double Bell potential. It is centered, one has to apply half of flux quantum to this loop to achieve this situation. That was the idea how to put in practice. It's not practical to make the inductance loop. And in this design, well, Delft design, it's my institution, it has been replaced by two Josephson junctions. So in fact, there was a three-junction Delft flux qubit. What are superposition states in this junction? They correspond to two wells in this potential. If one looks at just geometrically, those have been states with opposite current circulation in this device. Either clockwise or counterclockwise. Two superposition states. And again, that appeared to be a valid design. However, it still suffered, in this case, from flux noise. Right, so finally, look, I'm a theorist. I'm very eager of rather complex toys. But if one looks at practical applications, it's a law of, I wouldn't say stupidity, but the law of simplicity. The most practical device, the most practical from technological perspective, appears to be the simplest one. That's how we come to transmon qubit, which at least at the moment is the winner of qubit competition. What remains from Josephson junction? In fact, yeah, I sketch again this potential, cosine potential in space of phase. And there is a quantization, which anyway, for this parameter range is not very different from quantization in an oscillator. However, this oscillator is a slightly nonlinear one. What does it mean? It means that this energy difference differs from this one by about 10%. And that appears to be enough for qubit applications. Again, one takes these two as logical state of qubit and then applying pulses with different frequencies. One achieves measurement of the qubit and qubit manipulation. What makes it so special and why it is such a fancy title, official translation of this title, is a transmission line shunted plasma oscillation qubit. Plasma oscillations correspond to energy quantization in this well. And transmission lines means that these qubits are physically placed onto a transmission line. Right. It is, this design has been pioneered in Yale in 2008, I reckon. Yeah, something around that. And the fact that they put it into transmission line appears to be very productive with respect to qubit coupling. Just inductive coupling through this transmission line, sharing the transmission line, provides necessary coupling between the qubits. Once this has been achieved, the number of qubits we can operate with become to grow from year to year. Okay, I guess it was the first 2-qubit processor in resonant cavity. That immediately brought up some engineering questions. One would have to make a good cavity to isolate the transmission lines from external noises, simultaneously keeping up the operation. Once this engineering problem has been solved, it went on 3 qubits in 2010, and well, it goes on, and look, it has been already industrialized, and then, you know, the number of qubits, it's not already what you read in scientific papers. It's something which you read in news, fortunately or unfortunately. And the scientific information is either top secret or is so much applied that it doesn't make much sense for a physicist. There was a question, is there transform based on the infinite potential representation of the phase operator or on the Cooper Island periodistic boundary conditions? The latter, right, one can see it here. So these points are eventually come together. It was a superconducting island, which is just attached to the transmission line. So it's finite number of charges involved. But as you see, it's not really terribly important because any nonlinear oscillator would do the job. It's not really profitable for me personally. I could say it doesn't have to be Josephson. It doesn't have to be superconductor. Superconductivity and Josephson effect just provide. Gap in superconductor provides the absence of dissipation. Noise provides the coherence which we need. And the energy scales of Josephson effect just put it into frequency scale of microwaves, something which is relatively easy to engineer. Good. I guess I'm done. Take-home message is evident. Combining Josephson energy and Coulomb blockade, we have quantum devices. You can describe with Schrödinger equations. There are two limiting cases. There are many, many possibilities to make qubits out of that. At the moment, we have a single solution which seems to be most technological at the moment, but you know, technological also changes from time to time. When I was young, the best of technology was actually a vacuum tube, but already in several years it changed to transistors. So perhaps future generations would find new possibilities in the same quantum Josephson physics. All right, I think I'm done with my presentation. Questions, please.
So first of all, thank you very much for your very detailed and very pedagogical lecture. And so I think we have also time for questions.
Yeah, one can just, since it's not a presentation, so one could just speak up.
Yes. Mm-hmm. So you can expect that since everything is recorded, and maybe you can get what we can encourage our participants after listening to this lecture, maybe again online, to send questions to Professor Nazarov by email, if you don't mind.
Yeah, sure. I would encourage this.
So that may be also good after some thinking it over at home. And sometimes questions come later.
Good. So I stopped my screen. I guess Professor